Well, hello and welcome YouTube. This is Mr. Robinson again with yet another discussion video. Week numbers 12 and 13 focused on radicals and graphing quadratics. Here are the 10 questions that are asked and are going to be answered. They're a little uneven this time, and by that I mean that there are only 2 questions focused on graphing, and both of them have to do with the vertex. Not too many questions asked for me here. When it came to the people who did ask, if you know, based on my groups that do ask questions, my two even class periods were able to ask questions 1 through 8. My one other class period asked questions focused on 9 and 10, and they had some questions based on here as well. So again, a little uneven, not a lot going to be on graphing here. I'll see what I can do, and of course I want to keep these as short as possible, but I'm just going to go ahead and get started here. Prior to that, let's just make sure that you know how to get a question asked and answered here online. It's really quite simple. You got to submit an assignment sheet at the end of a week. And when you do, you ask 1 to 3 questions down here. The questions must relate to the topics in the weeks that are being covered. I will select up to 10 questions that I feel are best to be answered for the masses. Now again, not too many graphing questions were asked, and some other ones really just not something that really needed to be answered on here, at least not compared to some of the other ones here. And those who get their questions selected will receive a 6 out of 5 on their question for that 2-week period. A nice little extra credit bonus point there is pretty good incentive for some people. Let's go ahead and get started. And the first question here, question number 1, multiplying radicals, how do you do that? What does it mean to have them? Well, I'm going to start off with 2 properties for you, and I think it'll pretty much take care of all of it, but I'll get some examples done along the way, probably in some other questions as well. First and foremost, a property showing the square root of a product here. It is true, indeed, that you can split this product into 2 square roots and multiply both of those. So that's one of the things here. These are interchangeable in that you can do one to become the other and vice versa. This doesn't just split, this also joins. And there's plenty good reason to go from this to this, of course. That's when you simplify them. But to go from here to here, that's going to happen quite a few times as well. Think about if they ask you to multiply 2 things, or if you do maybe some prime factorization. I'll talk about that again. But if you have some prime factorization, maybe you have an answer that says 5 root 3 root 5 ultimately, and the end goal in simplifying is to have only 1 square root, so you multiply these 2. It becomes 3 times 5 inside 1 square root, which is 15, and 5 root 15 becomes an answer from something that was being done up top. So that's one of the properties here to really focus on, is that you can split this up and you can join them together. And by the way, just to make mention of it right now, because division and multiplication really fall under the same breath, if I have a fraction here inside a square root, I can indeed split that up as well. And I'll be sure to be talking about that when we talk about rationalizing denominators. Now, what's not true and what's not okay is you cannot split up a sum into 2 square roots like this. And vice versa, this cannot combine into that. It cannot. I've talked about that in class plenty of times. And same with subtraction. You cannot subtract these and split them up as well. So multiplying radicals, how do you do that? Well, just like this. You join them up. And I assume you're talking about from this way to that way. They go up under one number, just like this. Now, a second property that I just want to make mention of, which this kind of covered it right here, but maybe sometimes you just need to see or hear more about it. A second one here is that if you have, say, 2 different radical terms like this one, and it multiplies with another one like this, well, what happens is that the rational values A and C multiply together, and then the irrational values B and D multiply together. So this would become the result of this, just like these 2 would multiply here. Now, how else do I know that? And this last answer is the last thing I'll address here. Everything here that you're looking at is multiplication. When you saw 5 root 3 root 5, that is indeed 5 times root 3 times root 5. Even if the appearance of multiplication is not there, it does not mean it's not multiplication. So this is A times the square root of B times C times the square root of D. And multiplication is commutative. So what I could have done in between these steps here is brought A and C right next to each other in this multiplication, and then multiplied by this root B and by this root D here. And then a times c is the same thing as ac. And root b times root d, as you well know, these two would fuse together inside one square root, and as they multiply, you don't need to write the dot in between. But the one take-home thing I need to say about all of this is that all of this is multiplication to begin with. Even this fraction right here is multiplication. You should know that, if I take one or the other here, this is root a times 1 over root b. I mean, all of this is multiplication when all is said and done. These are not multiplication. They have that plus and that minus sign. These are not. That's a different story, but everything else is. So if you put dots in between, maybe your perception of these problems will change a lot more. But this is one property that is must known, and this kind of carries on with it to make sure that you understand that. Okay, question number 2, what is the fastest or easiest way to simplify a radical? Well, there are two different things you're stating here, one fastest, one being easiest. Sometimes an easiest is someone's fastest. Let me just break up this into two different categories. One of them is factoring out perfect squares, so perfect square factorization. And I'll tell you right now that this is my go-to for the most part, almost always. And the other one is prime factorization. So if you're going to ask which one's easier, arguably prime factorization is easier. Now, its best case scenario of you breaking this up into something is going to take a little bit of effort and time. You have to write some things down. And this is going to come into play into a later question that's being asked here. But for prime factorization, even if I wanted to take something like the square root of 32, here, let's do another, like 40. I don't know. The square root of 40, you start breaking it up into factors that multiply into 40, and all these would have square roots. So something like 2 times 20, and 20 can break up into something like 2 times 10, and 10 can break up into something like 2 times 5. So you write all this stuff out, you figure out that these are prime factors here, you multiply them together, and then any pairs, this is another property, but any pairs of square roots that multiply together, like this, just become the value that's inside. So the square root of 2 times the square root of 2 is 2. And this goes back to what I was talking about before. This is why I wanted to bring up a problem like this. This isn't fully simplified yet because these aren't under one square root. So I multiply them back together and I get 2 root 10. That'd be my answer. But, in prime factorization, maybe you just keep dividing by 2 until you can't divide by 2 anymore, until the number is no longer even, because that's an easy way to do it. You can keep doing that. And of course, if the number's not even, then you got to check, can I divide it by 3 or 5 or 7? But you keep going that way up until, you can't go anymore. And then anything that's left inside is simplified. And that's an easy way. But again, even in a best case scenario, it will take up some time. Perfect square factorization is just factoring perfect squares out of values. So if I take the square root of 40, I ask what perfect square values can divide out of there, and I seek those immediately. So for instance, 4 can divide out of 40, and 4 is a perfect square, and in fact, it's the largest perfect square. So instead, I say root 4 times root 10, and the square root of 4 is 2, and I get 2 root 10. And 10, I know, doesn't have any perfect square factors in it. I can't divide it by 4 or 9 or 16 or 25. So that's my result. See, here, even when I got to root 10, if I'm just playing the prime factorization game, I got to split these up. And really, there's another reason for it. I'd have to think of another value to really make mention of it. But there might be another root 2 that's lingering somewhere, or another root 5 that's lingering somewhere in your prime factorization tree that you got to address. So you have to make sure to take care of those early on. Now, so I call this one the fastest, and really I don't have to write anything going from one to the other if I know what I'm doing there. I don't have to store more than 2 numbers in my head at any one time. I divide this by something, and there's a resulting value, and then I take the square root of that value, and that's it. Now, so that's the fastest way to me. To me, it's normally the easiest as well. The times when it gets harder, though, is when in perfect square factorization, if there's more than one perfect square factor. So we just saw the square root of 40. How about something like the square root of 80? Well, the square root of 80, see, I can divide this one by 4 as well. And I get root 4 times root 20. And then root 4 is 2, so you get 2 root 20. But I'm not quite done yet because, and this is going to answer another question later, because this has perfect square factors in it still. You can get another root 4 out of there. and root 4 is 2. And again, as I said, this is all multiplication, so this becomes 4 root 5. So that took some time, and I had to write some things down. That's 4 times root 5. I had to write some things down, so it wasn't necessarily faster than prime factorization, because this would have just been one other tree branch, 2 times 40, and then it would have broken down like this. But, if you know any other larger perfect square factors that divide out of this value, it shouldn't take any time at all. For example, 80 can also divide by 16, and root 16 times root 5 gives you 4 root 5, and there's the answer, and I didn't have to do much as long as I knew that it divided by it. So this to me is the fastest way if you know what you're doing. Get out the perfect square factors and then you're done. The easiest way is probably this, as long as you know how these things join together, and then you're all taken care of. But this isn't necessarily faster, and this can be easier. It depends on your idea of computation and understanding what's actually happening as you break this stuff up. Okay, question number 3. How do you know that you have fully simplified your radical terms? Well, basically, the way that I just said it before, if you're doing perfect square factorization, the way that you know is that there are not any more perfect square factors inside your square root. No more. I'll write PSFs, perfect square factors, are in the root. In this case, a square root. So remember when we saw something like that 4 root 10, I forget if that was the number. Let's pretend 4 root 10 was the answer. I think it was 2 root 10, but that's okay. If you see 4 root 10 and I ask you, can I keep simplifying this? The only question really is, does this number have perfect square factors in it? Not does it have factors in it. That's a different question. It's not asking, is 10 a prime or composite number? Now, there's one thing to know for sure. If you have a prime number in here, it for sure doesn't have any perfect square factors. But even some composite numbers like the square root of 10 doesn't have any perfect square factors, because the only thing it can divide by is 1, 2, 5, and 10. And those numbers are not perfect squares. Our perfect squares are 4, 9, 16, 25, 36, 49, 64, 81, 100, 121. And you know how I skipped on 1 because I don't care to divide by 1. That's not what I'm talking about. So that's fully simplified there, and I can tell from perfect square factorization with that. And it's not necessarily just small numbers that do that as well. Think of a number like what if your answer was 9 root 86? 9 root 86, and you tell yourself, because I might do this as well, you're like, this number is so large that surely one of the numbers can divide by this thing. Truly, you can divide it by a 4 or a 9 or a 16 or something like that. Actually, that's not the case. And this is where prime factorization sometimes comes into play pretty well. If I divide this by 2, I get root 2 times root 43. And these are, root 43. And these are both prime numbers. So clearly, as these are both prime numbers, then these are not perfect square factors with this. And as they're prime numbers and not identical, and that's what I'm going to talk about next year. Even square root of 186. You're like, well, surely there's something that can work there. Well, no, because that's 2 times 93, and 93 is 3 times 31. And those are prime numbers. None of them are pairs. So this is even not a prime number. This doesn't even have perfect square factors in it. So if there are no more perfect square factors in the root, then you are fully simplified. You're done, taken care of. Even a small number like 8 has a perfect square factor of 4. So you keep going with that. You change that to root 4 times root 2, which is times 2. So 18 root 2. Boom, like that. And of course, like I said, you can go from here to here pretty quickly if you know what you're doing. Take the square root of your number and multiply it, and you're good. But numbers that are very small might have perfect square factors. Numbers that are very large might not. And that's just the result of this. There's nothing really else to say about that. That's it. That's with perfect square factorization. When you finally realize that this number has no more perfect square factors, then you're good. Now, the other one, and I've kind of brought it up when I was talking about these things right here, root 2, root 3, root 31. If you're doing something like prime factorization, and remember, you don't have to do one versus the other. You can combine one with the other if you feel more comfortable once you get to smaller numbers. But prime factorization, there are no duplicates. And that's really what I was getting to when I was bringing up these square roots right here. I wouldn't write my answer like this. I would write my answer like this because I don't want multiple square roots in here. Now, if I split this thing up, and if none of these are duplicates of each other, that means there are no perfect square factors, right? If I had an extra square root of 31 broken up into here, that means these two would combine back and become 31. That means whatever 31 squared is, that value was a perfect square factor of the larger value at play. And I wouldn't have to do prime factorization to do that. I could have. Just like this 9 root 8 right here. Instead of finding a perfect square factor of root 8, I could have broken up root 8 into root 2 times root 2 times root 2. Now, that's not to say that just because these are all square roots, you join them back up again. No, first you take a look and say, okay, I want to make sure that I take any duplicates and I pair those up. That's where I get my 9 times 2 root 2, just like right here. And then that becomes 18. So if you break this up more because maybe you don't know if there are perfect square factors that exist in your number, like this was a fair one to try, then you check and see if there are duplicates, and if there aren't any, then you bring them back together. But if there are, then you take it out of the perfect square right there. So how do you know you fully simplified it? No more perfect square factors, or in prime factorization, there are no more duplicates. Now this is true for variables as well, and I know a variables question will be coming up later, so here we go. Question number 4, should you always simplify first no matter what? There should be a question mark there. No matter what. Almost unequivocally, yes. The main reason for this is so, number 1, you are avoiding larger numbers to deal with if you have to. I remember one time we were dealing with a problem, and I don't remember it exactly, but let's pretend it was like 2 plus, I remember these numbers, root 40, and there was another number that was like a root 28. And I don't know what these other numbers were over here. I'm not really concerned about them. But should you decide to, say, FOIL, by distribute and multiply and FOIL like this, at some point you're going to be doing root 40 times root 28. Now that number is a square root of 960, so you would have to find perfect square factors of the number 960 or do prime factorization of this large number 960, which by the way, perfect square factors do exist here. So you'd have to be doing that up until you satisfied yourself with what you do, and that takes a long time. So what I would do instead when it comes to this is I would simplify the square root of 40 into, remember, root 4 times root 10, that's 2 root 10. And I would break up root 28 into, I guess, is 2 root 7 right here. Then I would multiply. And when I FOIL, eventually I have to do 2 root 10 times 2 root 7 somewhere, and that becomes 4 root 70. And you have to make sure that now after that, this number doesn't have any perfect square factors. And one way you can do this, and this is how I'm going to bring this up in just a moment here as well, one way I can do this is I can break these up into their prime factors, like root 10 is root 2 times root 5, and root 7 is there, and because there are no duplicates, I think you're good to go. So this is the simplified version of this number times that number, root 40 times root 28, and I think I probably did that a lot more quickly than I would have in dealing with larger numbers. So that's one reason that I would be doing those first. I should be simplifying first. A next reason, and I'm going to try and make some numbers that work within here. Let me just clean this up right here. Another reason is because if you have addition or subtraction coming into play here, you might want to see if like terms can combine prior to doing anything else. And of course, ultimately, you're going to have to check that anyway. So what if I had something like 3 root 10 right here, okay? And over here I had something like, root 7. I'll just make that up. So then that becomes 3 root 10 plus this was 2 root 10. And then here this was 2 root 7 plus root 7. And what happens? I get to combine like terms. 3 root 10 plus 2 root 10 is 5 root 10. And that's going to multiply with 2 root 7 plus 1 root 7. That's 3 root 7. And then I get my 15 root 70 and I'm done. I didn't have to FOIL right here because I could combine like terms. And that's the matter of the problem, right? Is the problem set up conveniently enough for you to do that? It depends. But you test it anyway because you get smaller numbers as a result. And they might be able to combine. And I mean, I think it just works out better for you if you're able to do that. Which is also true with division. If you have something like root 40 divided by 28, you can simplify this fraction if you'd like to. And I'm going to talk about that kind of stuff more. But you can also maybe try something like this along the way. Remember, this was 2 root 10. and this was 2 root 7. And these 2's can cancel each other out. Now you have root 10 over root 7, which is not the answer. I'd have to rationalize the denominator. But something could cancel before that maybe couldn't cancel prior to, that you couldn't see. Or maybe you could. I mean, the point is you don't yet know until you really play with it a little more. So there's that. Now, like I said, unequivocally, yes. Almost unequivocally, yes, you should be simplifying first no matter what, which is a great question. Now, there was a problem, and I think it was this. I'm going to just write it out and see. 3 root 12 times root 6. This was a problem that was on one of the things before, and, your question, you might be asking yourself, should I simplify this first, fully? Because let's see what happens if you simplify it first. Root 12 can simplify into 2 root 3. So I'm going to do 3 times 2, which is 6. I'm going to do root 3 times root 6, which is root 18. And you'd think you're done maybe because you broke up the one thing that could be broken up. The thing, though, is that root 6 is root 3 times root 2. And as you can see, there's a root 3 there. That means that a root 9 can factor out of this value. See, this can become 6 times root 9 times root 2, which is 6 times 3 root 2, which is 18 root 2. Now, that took a little more steps than what was needed. If you're really good at what you're doing here and you understand all the properties and the math that's going on, you could do something instead like this. I know that root 6 and root 2, although factors of root 12, are not perfect square factors. I'm well aware of that fact. But if I break it up into these two, I'm doing that because there's another root 6 right here. And these two can multiply to become 6. So 3 root 2 times 6, which 3 times 6 is 18. So I'm doing that because I'm trying to match one up with the other if I know that I can do that. And that took less time, actually, than this one. So there are times, if you know what you're doing with your math and if there are multiple numbers there that can help, do things in your favor, you can take care of that. You just have to know what you're doing with it. It's going to take some time, take some practice. But otherwise, otherwise I'd just say yes. Always go with it. When in doubt, just, simplify it out. Right? I totally go for that. All right, number 5. How do you keep your numbers and terms organized when dealing with multiple prime roots? Example, square root of 30 is root 2 times root 3 times root 5. Well, to answer this specific question, I would just say exactly as you kind of wrote. Write it in ascending order. And I'd have to come up with a big number to show you what I'm talking about, but if you don't have it in ascending order, you might not know where your pairs of values are that can duplicate. So you just do that straight up. So let's say I take, I have to think of a number for you. This isn't going to work out very well. Let's hope that a number like the square root of like 240 really has some nice, big, perfect square numbers in it. Let's say I do prime factorization because that is what this individual student was kind of asking about here. So root 240, I'm going to start kind of breaking it up into kind of different numbers, like say root 40 times 6 times root 6, something like that. And then root 40, maybe you're like, okay, that's root 4 times root 10, and root 10 was root 2 times root 5, and root 4 was root 2 times root 2, and root 6 is root 3 times root 2, and I've broken everything up now. So I've come up with my values. These 6 numbers right here, when multiplied together, become 240. 2 times 5 times 2 times 2 times 3 times 2 is 240. So root 2 times root 5, all those multiplied with roots, is root 240. Okay, so if I write this out, that's root 2 times root 5 times root 2 times root 2 times root 3 times root 2, and that gives you 240. And the problem is that these aren't really organized the way that I'd want them to be organized. It would be best if I write them in ascending order. So that means let's find all of our root 2's. There are 4 of them. So root 2, root 2, root 2, root 2. Then let's find all our 3's. There's 1, and then the last remaining numbers of 5. So I think that's the best order you can put it in, because now you can find pairs of values should they exist. There are these pairs of root 2's, these pairs of root 2's, and then these don't have any pairs with them. So I'm going to do 2 times 2 times root 3 times 5, if you remember, which is 4 root 15, and there ends up being your answer. I think that was one of my things I wrote before, 4 root 15. Apparently that was root 240. But yeah, so the organization right in ascending order. I think that's the big principle there. Now, your question made me think of another question that was even bigger than this. And the question I want to really ask, I want to really answer based on whether or not it's asked is, how do you keep your work organized when it comes to simplifying radicals? Okay, how do you keep your work organized when it comes to simplifying radicals? Well, one way is kind of things like this, cross things out and make sure they're written down in a different way. A second thing could be, using those dots with multiplication. I've talked about that before. Really make sure that when you're dealing with some sort of problem that has simplifying radicals, you understand everything is multiplication. I don't have good examples, again, off the top of my head when I deal with these things here. Let's try a number like square root of, I don't know if this is going to work, like 424, something like that. So say I'm doing my perfect square factorization. Okay, one thing I might do is, again, keep my work organized. Anything that I write has to be equivalent. Remember what it means when you simplify a radical. The value needs to stay the same. Nothing can change there. So maybe, on the side I'm writing perfect square factors, and, stating on the side is really a key concept here. Whether or not I find the largest perfect square factor, which in this case, my aim is actually not to do that, so I can show you more organization tactics, then, you go with them. You can keep listing perfect square factors up until you've maybe reached or exceeded half of this. I'll just go up until, say, I run out of room here, like 144. But I'm not going to do all these anyway. I'm just going to keep testing this along the way. All right, can this divide by 4? I believe it can because 400, let's not do 424. Let's do root 432. I think that'll be a little better. But this can divide by 4. So this is the square root of 4 times the square root of 108. And, one of the things I talked about here before was really use those dots. Really make yourself understand that every single time you do something here, it is multiplication. That's a nice way to keep things organized and cleaned up. And by the way, another good important thing is the number that you're trying to factor out, one of these perfect square factors, write it first. Write it first because that's the number that's going to come out of the square root. Square root of 4 is 2, and now I have 2 times square root of 108. And that helped clean things up a little bit more just because it was already in front. Imagine if instead I wrote root 108 times root 4, and that becomes root 108 times 2, and now that's starting to look a little weird. You might even convince yourself these can multiply together and that it's affecting it somehow. You don't want to do that. Try and avoid that kind of mistake. Now, 108 may not be done because there may be perfect square factors that exist in it. In fact, I know that 9 can divide. I know that 4 can, but let's deal with another number. 9 can divide out of it. I don't know if it's the largest one. It looks like it's not. 9 times 12 is 108. So again, every single value, root 432, every single value is the same so far. This and this are equivalent, numerically so. These have the same value. These have the same value. The square root of 9 is 3, and what's important here with these dots, I'm going to multiply 3 with 2. Now, square root of 12, again, square root of 4 can come out times again. Square root of 4 is 2, and I don't know why I didn't multiply these together yet, but that's okay. And 2 times 3 is 6, times 2 is 12, so I get 12 root 3 as my final answer. And I mean, it depends on the problem type. There's a lot more than this that people have issues with. What if there was another number in front to deal with? What if you were adding with something else? These are clearly the easier kinds of problems, even if it's large. Clearly was an easier kind of problem. But the point is that everything there stays the same in terms of value. What if there was a 6 here in front the entire time? Well, that means 6 will always multiply with whatever's there. 6, 6, times this. And, I probably would have multiplied this early on. But 6 times 2 times 3 times 2 is 72 now. And that would be your answer based on that. So a couple things you can do. The big one is the dots. The other big thing is making sure every value that you write matches up and maintains. You can also do things like these arrows. Now, you don't have a lot of different colors like I do, but really bringing about where certain values go. Like the root 4 turned into this 2. That's why there's a 2 here instead of root 4. These are here instead of root 108 for that reason. And, you go from here. Root 9 is 3. That's where that came from. This split into these two. This turned into this. these 4 values here turned into that 1. You can do arrows. That can keep you organized as well. A lot of different things. A lot of different ways that you can cope with this stuff, There's a lot of different tactics. Now, again, this isn't one of the harder problems. And, of course, I don't really prepare beforehand what kinds of difficult problems that can arise based on this. But, there you go. I'm obviously going slowly through all this, so I want to keep moving on. All right, question number 6. How do you simplify radicals that have exponents? And I think you're talking about variables. I think you're referring to variables. So things like the square root of, x to the 6th power. Well, there's a basic principle behind it, and is that as you're dealing with square roots, that means this value is a 2. And you may know that roots can be rewritten as exponents with a fraction. And you may know that these two exponents multiply when all is said and done. And as you know, 6 times 1/2 is 6 divided by 2, which in this case is 3. You don't have to do all those steps, but what you probably want to know is that this right here is the same thing as this right here. When you take the square root of a value, you divide the exponent by 2. That means that the square root of x to the 100th power is x to the 100 divided by 2, which is x to the 50th. That is for exponents. Again, that is for exponents. Now, what if your exponent is odd? Well, let's take something like the square root of x to the 13th. See, you would do x to the 13 divided by 2, and you'd say, oh, that's x to the 6.5. Do I just write that? Well, no, we're not going to have half of something there. But, if I think about, because I didn't talk about this in class, so let me do this way. This is also x to the 6 plus 0.5 power, which is x to the 6 plus 1/2 power. And when you add exponents, that means that's two things multiplying with the same base, x to the 6 times x to the 1/2. And as you know, 1/2 power is square root, so that's x to the 6 times the square root of x. And that's actually the answer there. So it's the same thing as before with values. You factor out perfect square factors only. The only perfect square factors of variables that exist are are variables with an even powered exponent. How else can I take the square root of something if I can't fully divide it by 2? And how can I divide by 2 if I have an even number? So a better way to write this instead is I would just factor out x to the 12th power from this, and all that's left is one more power of x. Remember, these are multiplied. X to the 12th times x to the 1st is x to the 13th. And I can then divide my 12 by 2. And remember, this is still inside a square root. That doesn't change. 12 divided by 2 is 6, and I get x to the 6 times square root of x. So ultimately, how do I simplify them? I divide my exponents by 2, and I first treat it as an even value prior to that if it's not even to begin with. So that's a pretty straightforward concept. Now, it gets a little weirder when there are a lot of numbers in the way. And, maybe I, do a super combination of a lot of different values here to make this a little more compelling. Right? What if I have something like, the previous number we had, that root 432? Okay, let's take that and, let's run with that a little bit. Let's say I do have a 6x squared on the outside of a square root. And I have a square root of 432x to the 19th inside here. And I'm asked to simplify it. This might go back to one of those questions, how do you simplify these things? Well, this may be the last big one I'm going to play with. And after that, it's kind of all just other things here. First thing I might do is I might really recognize the fact that everything here is multiplication. So instead of looking at the problem like this, let me do this downward. Let's write dots in between everything. 6 times x squared times, and I'm going to split these two up. The square root of 432 times the square root of x to the 19th. Remember, these are factors of each other, obviously, because they multiply together to become this, but I deal with these separately. I simplify this in a separate way that I simplify this. So, maybe I do one at a time, or maybe I just focus on one part of a time. Don't make this big workaround thing. Just go ahead and keep going. Maybe that you can divide this number by, for now I would still say I know I can divide this by 4. So square root of 4 is 2. So I get 2 root divided by 4. I get 108, right? That's there. Times, and again, I'm going to split apart an x to the 18th power and be left with a root x right there. because I know that I can be dividing this one by 2 here. So that's 6 times x squared times 2 times, and I could divide this by 9. I could divide it by 36. Root 36 times root 3, so that's 6 times root 3. This, I divide the 18 by 2, and I get 9 outside of the square root, and there's root x. Now everything that I could pull out of radicals I did. The square root of 3 is a prime number. The square root of x, obviously, I can't simplify that either. So I've taken care of all that I could inside the radicals. Now what's left is cleaning this thing up in some sort of way. Remember, multiplication is commutative, so I can rewrite these in a way that's beneficial to me. Like, this 6 can multiply with this 2, which can multiply with this 6 right here. And let's get these x's together. This x squared can multiply with this x to the 9th. And then this root 3 can multiply with this root x. So my end result, 6 times 2 is 12, times 6 is 72. So I'm going to get 72. X squared times x to the 9th is x to the 11th. And the root 3 times the root x becomes root 3x, just like that. And that is the final answer right there. And what that means is this value and this value are the same thing. And I've pulled out all my perfect square factors in the end. So that's keeping it organized. That's dealing with radicals and exponents. I know I'm answering more than one thing at a time. I'm not very good at prepping this stuff for you. I'm sorry about that. But, in terms of taking care of these things, I hope it's addressing everything. And you're seeing a lot of different approaches to this. And again, this is where arrows could come into play, but it starts to look kind of weird, even with color coding it in a way that's like, all right, there are my numbers. Here are my variables, at least the rational ones. Boom. And then here's this number, and maybe here's that number. Right? So you're taking care of everything that way, and then, maybe these combine to become this number, and these combine to become that number, and then, these combine to become that number there. So, there are a lot of different ways in terms of organization here, but the radical thing, you're dividing your exponent by 2, and if it's an odd number, factor one of them out. It won't have this won't be a perfect square factor. You'll be left with the root x somewhere, and we'll just have to take care of it as is. Question number 7, how do you rationalize the denominator of a problem? Okay. First of all, let's understand what rationalize the denominator means. It means no irrational values in the denominator. Why? That's that's for a different day. We've done some things with it before, but denominator. But eventually, just no irrational values there. So, you can't have something that ends up as like a over the square root of b, and b is an irrational number. So how do you rationalize it? Well, it's really just all about two things. Because here's one way. You have to multiply. Here's how you do it. You have to multiply by 1. That sounds weird. You're like, multiply by 1? That's not going to help. Well, you don't truly multiply just by 1. You multiply by a value that is equivalent to 1. In that case, that means multiplying something divided by itself. When you have this setup right here, you would multiply top and bottom by the same thing. In this case, I mean the same thing as the denominator, because as you saw a lot before, the square root of b times the square root of b is b. And that's what's going to rationalize this thing, multiplying it by itself if that's the only term there in the denominator, just like that. Now, why do you do this? Well, again, they don't want anything in the denominator here, but this looks more confusing than this, doesn't it? Well, to some people it does. It does give more benefits when it comes to cleaning some things up. Like, for example, you might have something that started off by saying 12 divided by root 3. So when I rationalize this, I'm going to multiply top and bottom by root 3. And, both of them. And root 3 times root 3 is 3. So I have 12 root 3 divided by 3, and now you're left with dividing. And just like you can only multiply rational values together, you can only divide rational values together. So 12 divided by 3 is 4, so you're left with 4 root 3 as a result. And, arguably that looks a little cleaner than that one does, and I don't know if it's just coincidence or not that allows you to do that, but that's still rationalizing it. My denominator is now a 1. Which is a rational value. Now that's one way, multiplying top and bottom by the same thing just like that when there's only that one term there. And by the way, even if, let's say there was a 2 out here. Should I multiply top and bottom by 2 root 3? Well, you can, but the point is to only multiply by the irrational value because that's what's going to clean this thing up. You don't need to multiply by 2 root 3 over 2 root 3 because 2 root 3 times root 3 is still 2 times 3. And then if that 2 is in the denominator here, that 4 over 2 becomes 2 root 3 as a result. And that's your final answer. Apparently this divided by that is that, which is kind of interesting. So it doesn't matter that there's more stuff in there in that one term. You just got to multiply by the denominator that's in that one term. Now, don't do it immediately, especially if it says something like 12 divided by the square root of 16. I shouldn't multiply top and bottom by the square root of 16 because this is not an irrational value. You can simplify this into 4. So this becomes 3. That's your answer. You shouldn't rationalize that. I mean, you can, but you're just going to have more work later on to do. And it's just, there's no real need for it, right? Ultimately, there's just a better way of going about it than what we've provided thus far. And the same thing with 12 divided by something like root 8. Should I multiply top and bottom by root 8 first? Or should I first clean this thing up? And by the way, there was something else I could have done here, and I'm going to show it right now. Should I simplify it first into 2 root 2 and then take care of rationalizing that? And I should probably do that. Now, this 12 can divide by this 2 and become 6, and then you can rationalize that. Multiply top and bottom by root 2, and you get 6 root 2 over 2, which is 3 root 2. So this thing simplifies to that, and that's just a part of the cleanup process. So that's one way you rationalize it, and there's more than one way as far as what you do here, but ultimately you multiply top and bottom by that value, but you can clean things up to begin with, and you can clean things up to end with, and that's one of the big things. So that's one of the ways you rationalize the denominator. Another way is, what if there's more than one term in the denominator? What if there was something like a over b plus root c? Well, if I multiply top and bottom just by root c, this isn't going to help because on the bottom here, even though root c times root c is c, this is going to distribute. Root c is going to multiply with b, and you're going to be left with this. Now that, I don't know if that looks more confusing or less. I guess because that's up there, it does. But this is still not irrational in the denominator. And you're like, multiply by root c over root c again. Well, you're going to get the same kind of issue here. Even though the top becomes rational again, that becomes a times c. Now the bottom is bc plus c root c. It's not really cleaning anything up, just multiplying top and bottom by the one irrational value. Now see, instead there's another way to do it here, and it comes through something we did in the last chapter, and that's when we were looking at difference of two squares. And what's cool about the difference of two squares is there's a middle thing that cancels out, which in this case is going to be very helpful for us. We have our a squared minus b squared being formed from doing a plus b times a minus b. Well, there's an idea here with irrational values and something else called imaginary values, where you have what are called conjugates. And conjugates are things that you multiply by that help eradicate irrational values in binomials, such as this a plus b times a minus b. I can do this. I can do like a b plus root c times b minus root c. And as long as I alternate this sign here only, I maintain whatever this sign was, and I alternate this sign right here, then my result, think about how this turns into that. On the bottom, my result is I'm going to be squaring b minus, I'm going to be squaring root c. And then on top, I distribute ab minus a root c. I mean, that all maybe gets a little weird, but on bottom, I get b squared minus root c squared is just c. So I get this right here, and I know this result looks weird. Of course, I can do a problem with you to show you it, but the bottom line is I have no more irrational value down here. I have rationalized my denominator. Whether or not the value looks good, it is now irrational. It is now rational. And that's the whole point behind it. So let's look at a problem like, and I don't know if this will clean up well or not. Let's do something like root 3 over root 2 minus root 7. And I'm just going to throw in a bunch of irrationals here just to make it kind of look weird. But the end result is, these can't combine in any sort of way. Too bad. So I'm going to have to multiply by its conjugate. I'll have root 2 minus root 7, plus root 7, divided by root 2 plus root 7. Again, as this was a minus, this becomes a plus. So on the bottom, what happens is I get root 2 squared minus 7 squared, or root 7 squared. that's 2 minus 7. On top, root 3 times root 2 is root 6. Root 3 times root 7 is root 21. And neither of these can simplify, so those will stay as that. So I have root 6 plus root 21 over negative 5. And this could be your answer. They might put a negative out in front like this instead. Something like that. And I know that this looks weird, but I've rationalized it. It didn't clean up to anything special. I didn't think much ahead of time regarding what would, result, but that's it. I've rationalized my denominator by multiplying by the conjugate. So the two different ways that you do this again is, multiply something by itself when there's one term there, or multiply that thing by a conjugate when there are two terms and one of them is irrational. And that's how you rationalize a denominator. Those are the two ways that really we're going to be playing with here. And of course, there is more cleanup stuff to be had at times. We just saw a couple up above, but down here I didn't really get a good one. But they do clean up every so often. Question number 8, how do I determine which method is to simplify radicals is best? Well, this goes back to question number 2. And I'm going to jump back to that one for a moment. What is the fastest, easiest way to simplify a radical? It's really up to you. I tend to find this for myself not only faster, but also easy. Well, the level of difficulty of this one, even if a smidge possibly harder, because here I can just keep dividing by 2, whatever, does not supersede the amount of speed I have to be able to do this. With the amount of ease I can do this, and with the amount of speed I can do this, this becomes a more efficient method for me than this one, no matter how much safer this one ultimately may be. Because it depends, again, on what numbers you have, whether or not you have the calculator, a lot of different things here. I know what I'm doing here, and it's a lot easier for me. To me, it's the preferred way to do it. That's how I decided. I can compute things pretty well. I know my perfect square factors. I know what I'm doing as a result of this. I can do it mentally. I can save myself time. That's why I chose this way. Other people maybe came in the class already knowing what prime factorization is. They understand this property enough that they're willing to do simple divide by 2 kind of division to pair this up and make sure that they just don't make any mistakes along the way, and that they, remember like question number 5, organize their work in such a way that they can really follow. And to them, their preferred method becomes to simplify radicals using prime factorization. Some people do a combination of both. You break it up until you try to decide, are the rest of the factors prime and something like that, instead of listing perfect square factors. A lot of different ways you can do it. How do you determine it? You got to first try both, right? It's just like my shoe tying thing. There are 3 different ways that I know how to tie shoes. There's the standard, and I don't know, it's from Big Daddy. It's called loop it, swoop it, and pull. There's the bunny ears method. And then there's, I believe, it's the way that I learned. I taught myself. I think they call it the Andy knot. And because I know how to do it, and I've tried the other ones. I mean, I've seen the pros and cons, and really the only con would be for shoe tying is if tying it one way made my shoes untie more often than another, then that might be a big deterrent. But even if one does only ever so more often, and there's another way that's significantly faster, regardless of anything else, then I would choose that shoe tying method. So again, I'm not really writing much here. I'm really giving these analogies here. I've tried all 3. Maybe I didn't give the bunny ears method enough practice, but that's because I found a sufficient enough way that I know even if I mastered the bunny ears method, I probably couldn't do it as fast as the way I do it, because you know that I can do that other one in like less than half a second. I can do it without even blinking. I'm talking about after you have those other 2 parts, tied together, like here, where you tie it underneath. You know what I'm talking about. And then I tie it together in that last part. So the speed with the bunny ears method, even if I could do it as fast, which I don't think I ever could, I think it takes me about 10 times the amount of time or more, I don't think that it helps my shoe stay tied even more together than the other way. So if that kind of makes sense, going back to this thing here, perfect square factorization, even if I could do prime factorization safely and never get problems wrong, I still probably couldn't do it as fast as this. Or the other way, even if I could do it as fast as this, or nearly as fast as this, you kind of know what I'm saying there, right? The whole point is, I don't get this way wrong enough. to sacrifice the amount of speed that I'd had to sacrifice to do it this way to get it right. In fact, I don't think I really ever get these wrong. I mean, yeah, every so often I will probably see myself get something wrong. But I don't think it'll probably be a result of me doing it this way. Now look, if the number's too large and I get stuck, then I'll start with dividing by 2 to begin with anyway, and that's just, that's blending them together. But I don't ever stick fully to this. I will teach it to open your eyes to it, and because it's something you've probably learned in the past. But eventually, just like factoring, I'm talking about quadratic factoring, look to try and do the mental factorization. Look to try to do the ones that will make your life easier. Take it from someone who's teaching you. I am your math teacher. I've been doing this for a long, long time. I've been doing it longer than you've been alive. What I mean is this. Literally, if I'm more than twice your age, and I've been doing it since I was your age or before that, then I've been doing it longer than you're alive. Take it from me, who's taught both ways, who's seen students learn this way and stuff like that. When you try it, stick with it for a while. You'll learn some things along the way and you will be faster at it. So, how do I determine which method to simplify radicals is best? Don't just take it from me that that's the better way. What I'm saying is take it from me to not give up on it and to expose yourself into the fact that you can get better at it with practice. But you got to know a lot of math to do it. So my final answer, if you know a lot of math and computation and you know your perfect square factors and you know what you're doing with these things, I would do perfect square factorization bar none all the time. If you've done prime factorization before, you understand how to divide numbers by 2, 3, and 5, and you understand the idea of pairing up duplicates of those quadratics of the square roots and stuff, stick with prime factorization for now, but keep practicing the other methods up until test time. And then when it's time for you to decide what you have to do, go ahead and do it that way. But when someone else is beating you all the time and you're wondering how I can do prime factorization faster, the answer might be maybe you can't do prime factorization faster. You just got to find another way to do it. Just like bunny ear. If 2 people are in a shoe tying contest and you're doing your bunny ears method, you're the fastest bunny ear shoe tire. I'm sure that's on YouTube. Fastest way, type your shoes, bunny ears. If that person's there, I doubt they can beat even a mediocre speed person at doing my Andy knot. And that's all I'm going to say on this talk right here. Okay, the last 2 questions are based on graphing and not too much about it, but question number 9, how do you know what numbers to put in your table after you find the vertex? Well, the basic principle of our graphing things here are the vertex is kind of the middle of the graph. And now it's not necessarily right on the y-axis, but it's the thing that shows the symmetry in our parabolas. If we have a parabola and we want it to appear like it's symmetrical on the left and the right, then the vertex is in the middle. So there's the vertex. No matter where your axes are. Your axes could be over here, and there's your vertex. Right? Actually, let me shift this up a little. I'm going to make a second case here in just a moment. So that could be your vertex. So how would I know to put my table? I put the vertex in the middle, for starters. So if this is an XY table, and if my vertex here is at x equals 5, I'm going to put 5 in the middle, and I'm going to build numbers around that. Generally so, you would look to go 1 over 6 and 7 and 4 and 3 and build as many as 5 points. That's what I'm asking you to do. Vertex in middle, 2 points on left and right. Plus, you can reflect points that way. Once you know it's in the middle and you have equal spacing from there, you can do that. There's something else about a fraction vertex that I'm going to jump into on question number 10, but I'll leave that for then. The other thing that you got to do, what other numbers to put in? Well, these might not be enough because what if this was 4 and this was 3 and this was 6 and this was 7? So 3, 4, and then 6 and 7. And then your other points are, here, here, and here, and here. Well, if you're trying to solve a quadratic equation, in other words, find out when they cross the x-axis here and here, I haven't tried enough values for that. So you'd have to keep extending here to 8 and 2, say. So maybe you try some other values like, maybe you know what the y-intercept is and you try that for sure. Or maybe you're far away from the x-axis. So maybe you go 2 apart. Maybe you do 7 and 9 instead of 6 and 7. Maybe you do 3 and 1 instead of 4 and 3. And you just keep spreading down until you know that you've found or passed the value 0. And then you work backwards from there. But the vertex has got to really be in the middle. I think that's going to be the big help with that. And again, you find the x value of the vertex by doing negative b over 2a. That will give you the x value of your vertex. And this is in reference to ax squared plus bx plus c. The opposite of the linear term divided by double the quadratic coefficient. And that'll give you this value here. Okay. There are other ways to do it. If you know your x-intercept, this is part of the 5-point method. Maybe you solve by factoring and you know the x-intercepts. Well, this number is split right in between those two. So there's another aspect of that, of course. Maybe this number is an 8 and this number is a 2. Halfway between 2 and 8 is the number 5. It's 3 over, or it's the average of 8 and 2. Right? A lot of different ways you can figure that one out as well. But the point is the vertex is in the middle. Everything else should be built around it based on that. And I'd really build symmetrically. If I'm going to go 1 away from here, like plus 1, then I should go 1 away from here the other direction, minus 1. Because once I've computed one value, then the other value reflects. It's the same height. And there you go. So that's really how I know what numbers I'd put in. It's all based on that. And again, I would keep building up until I find or pass my x-intercepts, because generally that's what we're looking for in our graphs, where they cross the x-axis. I think that's really one of the bigger highlights, at least. Now, sometimes they don't cross the x-axis. Sometimes it's something like up here, in which case, just build 4 more points. 1, 2, 3, 4. Give me that graph, and I think I'll be good. And the final question here is question number 10. If you are trying to find the vertex and it gives you a fraction and you can't divide it, what do you do? Well, that's a great question. Let's say you have something like x squared plus 3x minus 10 equals 0, and they're asking you to solve by graphing. Well, you have 2 ways to solve by graphing when it comes to this kind of problem here. One of them is just, using your negative b over 2a kind of thing. So like your x value of your vertex is negative 3 over 2 times 1, which is negative 3 over 2. And you can't divide it. And when they say you can't divide it, they mean that it's not an integer. Yeah, well, it's a decimal, negative 1.5. So like, all right, well, what do you do with this? Well, it's still a part of the graph. Keep this in mind. This is a normal kind of quadratic equation. This is even factorable. This is the second way I could have done this problem. I could have started with the x-intercepts. This factors to x plus 5 times x minus 2. And then your x-intercepts are negative 5 and positive 2. So our graph so far that I know, it crosses here and it crosses here. And what's halfway between negative 5 and positive 2? Well, it's not an integer. 1, 2, 3, 4, 5, 6, 7 away. So 3.5 away is the in-between, and it's right there. And that line is x equals negative 1.5, that value right there. So this doesn't land on an integer. It's unfortunate because it means you'll just have to do a little more calculation with things. But I'll tell you what it doesn't change. It doesn't change your idea of table values. It doesn't change your idea of symmetry. The only little fly in the ointment here, what do? Nothing. You do the same thing as you normally would. You go to x and y, you build a table with this in the middle. I can use negative 5 and 2 for sure because I know those are my x and y my x-intercepts. And as you know, as I talked to you about before, these are a little farther away than just 2 away from here. Other numbers you could build. What is half away from negative 1.5 in this direction? Negative 2. What's half away from negative 1.5 in this direction? Negative 1. It's not like I have to choose more decimal values. And I could choose 0, and I could have chosen 1 if I fit it, and I could choose negative 3, and all those. I could plug those in and compute them, figure out what they are. But if I still have to find the x-intercepts right here, you have to keep going a little more than that. There's only one you have to compute that's a decimal. The rest can be integers. You can reflect across symmetrically. Let me do some of these for you really quickly. We know that negative 5 is 0 and 2 is 0. They are both 3.5 away from my vertex. These are both half away from my vertex. I plug in negative 1. I get 1 minus 3 minus 10, and that is negative 12. So this is negative 12, so this is negative 12. I plug in 0, I get negative 10. I'm not plugging in 1, that's okay. So this is also negative 10. And all that's left is plugging in this one. And this one's not going to be great when it comes to a decimal unless you have your calculator, or unless it becomes a fraction that you know, and we know that negative 3/2 is that value. So the last point I'm going to make here when it comes to this is I'm going to go ahead and substitute this into here. Maybe you know what negative 1.5 squared is. Like I do, but that's me knowing numbers. If you don't, deal with fractions. Literally, you are going to have to deal with them at some point. The y value for this, negative 3/2 times negative 3/2 is positive 9/4 minus 9 halves minus 10. If I get a common denominator, multiply top and bottom by 2 over 2, multiply top and bottom by 4 over 4, I'm going to get 9 fourths minus 18 fourths minus 40 fourths. 9 minus 18 is negative 9, minus 40 is negative 49. So y is negative 49 over 4. As a decimal, it's negative 12.25. Negative 12.25. Doesn't really fit on here very well because that's 10. Let's call this 11 and 12. So somewhere like way down there. So let me plot that point for you though. I'm going to draw this graph. So there's that point. I dealt with my fraction. I did. It had to be so. And I dealt with it. And then these are negative 12 right here and right here. And these are negative 10 right here and right here. And I skipped my one and those ones, and there's those graphs, those points right there. So if I draw my graph, and this is not going to be a good looking one because I can't really connect these very well. But my parabola is looking, something like that. And it's U-shaped, and it's going up and curving and doing all its things in all its glory. But there's the graph. So you do have to calculate that this is not looking good. You do have to calculate that vertex value and just do the best you can. That's all I got to say about it. What do? Well, it's a number. A decimal is not a number. It's every bit as much of a number as an integer is. And that's something that some people try and, believe the opposite of. They're like, if it's a decimal, it's less of a number than another one. Well, no, not quite. 13 years old versus 14 years old may be a big difference. And 13 and a half may not be as big of a difference. Doesn't mean if you're 13 and a half years old that it's any less of an age than 13. You're just as close to 14 as you are to 13 now, the actual number. So, just like I'm getting really close to 30. So there's that. I don't really know what else to say beyond that because I just did some table things, talked really briefly about 5-point method and symmetry in between and the y-intercept. And by the way, corresponding points. These are both 1.5 and away. I think I talked about all I need to. I've way overstayed my welcome with this Q&A. I'm going to cut it off right here, and I hope you enjoyed it. Fiend!